This video tutorial is all about half-life calculations and the types of half-life calculations you will encounter in this course. Now, there are two types of half-life equations that you really need to know. The first one really determines the number of half-lives. This is usually indicated by the variable lowercase n, and the number of half-lives, n, is basically how old an element, the isotope is, so the total time elapsed divided by the half-life. Now, the second equation that you're going to encounter has a few more variables, and so the other equation you're going to encounter has NF is equal to Ni times 0.5 for half to the nth power. Now, NF is the final mass, Ni is the initial mass, and this n is the same n from above, the number of half-lives. Now let's go ahead and do several examples. The first example we're going to talk about is just determining the number of half-lives. So let's say you're given a sample of uranium-234 and it is 268 days old and has a half-life of 68.9 years. How many half-lives did uranium-232 undergo? I really like to do, in all of the examples that we're going to be going over, I like to use the problem-solving method. So the first step is always writing down what is given to you. So it's given to me how the time elapsed or how old an element is, and that is 268 days. The other piece of information given to us is the half-life, and that is 68.9 days. Now that's the only piece of information with numbers that's given to us. So we now need to know, what are we looking for? We are looking for n, the number of half-lives. If we're looking for n and we know the two other pieces of information, we can now find the equation that will solve for what we are looking for, and that is n equals time elapsed divided by half-life. Now, since I'm solving for n, I don't need to rearrange my equation. I can just plug and chug. 268 days divided by 68.9 days, and the days cancel out, and you should end up with 3.84 half-lives. Okay. In the next example, it states, if you begin with 48 grams of carbon-14, how much carbon-14 will you have left after 2.3 half-lives? So let's go ahead and write down what's given to us. So we're given the initial amount, so Ni, which is 48 grams. We are also given the number of half-lives, which is 2.3 half-lives. And so now we need to know, what else are we looking for? It says there we're looking for the final mass, and we don't know that quite yet. Now if we look at what's given to us, we know what equation we can use, and the equation we need to use, and the final mass equals the initial mass times half to the nth power, n power. And so we are looking for the final mass, so we don't have to rearrange this equation. We can just plug and chug. So here are my numbers: 48 grams times half to the 2.3 power, and that equals 9.7 grams. If you notice, I have grams here, so we should end up with grams as our final mass. Since this is going through a decay, my final number should always be smaller than the initial number. For number 2, example number 2, it states that you have a 55-gram sample of thorium-234, which is 144 days old. Thorium-234 has a half-life of 24 days. What is the original mass of thorium? So let's go ahead and write what's given to us. Since it tells us that it is 55 grams is 144 days old, we can assume that the 55 grams is our final mass. And we also know how old it is, so we know the time elapsed, which is 144 days. I'm just going to abbreviate that to D. It also tells us our half-life. So I'm just going to read half-life. That is 24 days. And so that's all that's given to us. Now we know what we're looking for. It says there the original mass, so our initial mass. And so we can go ahead and look at our last two equations. We know that these two make up N. And we know that we can figure out this, the initial mass, by using the final mass is equal to the initial mass times 0.5 to the n power. And n, since we know n, is equal to time elapsed divided by half-life, we can first solve for n before we solve for the initial mass. So if we do this, it's 144 days divided by 24 days, and you get 6 half-lives. Now that we know how many half-lives, we can go ahead and solve for our initial mass. In order to do so, we have to isolate this. And in order to isolate this, we have to divide both sides by 0.5 to the n power. So you end up with the final mass divided by 0.5 to the n power. And let's go ahead and plug in our numbers that we know. 55 grams divided by 0.5 to the 6th power. And so since we're looking for the original mass, we always know that our answer is going to be larger than 55 grams. So our final answer is 3,520 grams. Now, we've been solving problems where you're given the time elapsed and the time, the half-life, and you're either given your initial mass or final mass. Now we're going to look at problems that give you the initial and final mass, but we have to solve for either the half-life or the time elapsed. And this part requires an extra step and also requires the knowledge of natural log properties. So the first step we should really do is write down what's given to us. So I'm going to go ahead and write down what's given to us. This problem states that we have 65.2 grams of an unknown radioisotope that decayed to a mass of 15 grams. If the total time is 100 hours, what is the half-life? So our given what's given to us are the initial and final mass, 65.2 grams and 15.0 grams respectively. And we are also given the total time elapsed. And we are searching for the half-life. Now n, we already know, is equal to the total time divided by the half-life, but we're going to leave this part alone until after we solve for n. And how do we solve for n? We have to use this information. So let's go ahead and write that equation down. The initial mass is equal to the final mass is equal to the initial mass times 0.5 to the n power. And since we're looking for n this time, how do we solve for n? Let's go ahead and try to get 0.5 to the n alone. So if we do that, we can rearrange this equation. Now we have final mass divided by initial mass, and it's equal to 0.5 to the n power. Now, here is where you need to know the rules of natural log. Since this is half, we can go ahead and do natural log and put natural log on both sides. If we do that, our equation should end up looking like this. You have ln of final mass divided by initial mass equal to n times ln of 0.5. Now that we have n, we can get rid of this by dividing it on both sides, and you should be able to solve for n. And here's the equation for it. ln times the final mass divided by the initial mass, and all of that divided by ln of 0.5. And if you put all your numbers in, you should end up with 2.12 half-lives. Now that you know 2.12 half-lives, you know n, and you know the total time, we can actually calculate half-life. And all we have to do is rearrange this, and you should end up with this equation. The total time over half-lives equal half-life. And if you plug in chug, you should end up with a half-life of 47.2 hours. All right, so this final example, we have a sample of bone excavated from an ancient burial site, and it was dated using carbon-14 dating. It was found that the bone marrow contained only a quarter of the carbon-14 found in bone marrow today. If the half-life of carbon-14 is 5,730 years, how old are the bones? Okay. I'm going to go ahead and minimize the question at the top so that we have some space to work on. Now, what's given to us, it says there that the bone marrow contained only a fraction of bone marrow found today. It only has a quarter today, so we know that our final mass is equal to 1/4. So we're going to go ahead and assume that the original mass, and since this is a fraction, our original mass is equal to 1. And it's also giving us a half-life, so we know the half-life. And we have to find how old it is, or the time elapsed. If you recall, n is still equal to the total time over the half-life time. And so we're looking for this time, the total time. So I'm going to go ahead and rearrange this. The total time is equal to n times the half-life. Okay. But we can't solve for n yet. We have to figure out n using the other equation that deals with the initial and the final. So let's go ahead and calculate n using the initial and final. So we have the final mass equals the initial mass times 0.5 to the n power. Much like the last question, we have to rearrange this to solve for n. So if we rearrange this, let me go ahead and go step by step. You end up with the final mass divided by initial mass equals 0.5 to the n power. And again, using the natural log rules in math, I'm going to go ahead and put both sides in ln. Now that I have this, I can go ahead and solve for n. And if I'm solving for n should equal ln of the final mass divided by the initial mass, all divided by ln of 0.5. Let's go ahead and plug in the numbers. You end up with 2 half-lives. Now that we know n, let's go ahead and solve for the total time, and I'm going to use a different pen color for this. I can go ahead and just replace all these numbers. You have the total time is equal to 2 half-lives times 5,730 years, and you should end up with 11,460 years. And that is how old the bone marrow is today, or the bone fossil is today. So if you still have any questions, feel free to bring them to class, but do try those problems if you want to attempt the checkpoint problems on your own. And I will see you guys in class tomorrow.